This is the DDR demo session. Today's agenda is to cover the some of the topics actually from the our course. Okay, and here are the course content actually. What today's agenda is this. Okay, so we'll be covering what is actually DDR DRAM. Okay, what is the demand in the DDR DRAM in the industry actually? What is the demand actually we are saying in the DDR DRAM in the industry, and why this market is actually booming, and why we need this actually DDR, why we need to learn this DDR DRAM so that we can get good opportunities and all. So I'll be explaining them. Okay. And the next comes here is what are the applications of this DDR DRAM. Already you know, but yeah, I'll be going in some in depth and I'll be explaining some of the concepts actually. Okay, and uh, similar to that DDR, there are so many different technologies which are used in the DRAMs actually. So I'll be explaining them. Okay, with some examples actually. After that, evolution of those technologies actually, whatever I am explaining the technologies, I'll be explaining the evolution of them. Okay, and next I'll be coming what and all the courses we are going to offer, what and all the contents we are going to offer in this course, and next will be your doubt session. Okay. All good. And before starting that, anyone have any queries? Yeah. Guys, if you have
Uh,
any,
uh, yeah, Sachin here.
yeah.
So the sessions will be fixed time, or is it in the based on the trainer availability? Is it anything like
No,
that?
no, 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 no. No, the sessions will be fixed actually. So daily sessions will
Okay.
be going on. Okay.
Okay. So daily 1 hour it will be.
Yeah, daily 1 to 1.5 hour. Most of them it will be in the evening session only. I'll be explaining all of this actually. These are the actually points I need to cover while explaining the contents of the course. So no need to worry that I'll be covering that. Uh,
Okay.
so now, if
Okay.
you have uh, any troubles in joining the this session, anyone have any friends have any problems? I'm asking those queries actually. I can start it, right?
Yeah, you may go, Amit.
Yeah. Let's begin. Yeah. Okay. Uh, so actually, what is DDR DRAM? And before that, uh, uh, I'll be asking some questions actually. Who and all working in the actually DDR projects in your respective companies actually? Maybe anyone working in the DDR projects in your respective company? Yes.
Yeah, Amit. I was working in HBM.
You are working in HBM already. Yeah.
Yeah, yeah, yes.
Uh, High bandwidth memories, right?
Yes, yes. It's with the AI. Hmm. Yes.
Okay. 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 And any other questions?
Uh, Hello.
Yeah.
Yeah. Previously, I have worked on LPDDR5 actually. Current.
LPDDR5. Okay.
Yeah. That was like around 1 year. Yeah. Current I'm on.
Okay. Okay. Can I ask you some question actually? What is the reason to join this course actually? Yeah. Because
Uh,
already you worked on.
No, 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 no. I haven't explored everything there. Like it was a end of my project. Like there is no trainings involved that I have involved in, and then just it's a RAL based verification, and then just one feature verification. Like
Okay.
I audited just a small feature. Like I
Oh,
want to
okay.
explore
Okay.
more
That's a
actually.
common thing in actually companies, like, right?
Yeah,
So,
still.
yeah. 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 Please continue. Yeah.
And like one thing, Amit, and I have some theoretical knowledge on the DDR 1 to 4 versions. Like because
Theoretical
that is,
knowledge.
yeah, I know that burst shopping, everything regarding that. I
Okay.
know that,
Okay.
but coding part, I don't know. That's what interested in this. How controller will make that all things, right?
Okay. Yeah. Yeah.
Yes,
Yeah. Yeah.
yes,
Before that, before understanding that coding part and all, you should go thorough with all the theory parts.
yes,
Not only
yes,
that,
yes,
not only some concepts. So what happens in companies like whenever you join some DDR teams, they'll be
yes,
assigning some tasks to you. Correct.
yes,
You don't get a whole exposure. You need to
Yes.
study that part only, and you need to execute that part only. So
Yeah.
that's a problem in the industry parts, and they'll not provide any trainings at all. Apart from that, yeah, we'll start and we'll come to this later actually. These queries are there, so many queries are there. Actually, we'll come later. So hope and I got to know that there are so many people actually working on DDR projects in your respective companies, right? So I'm starting this course keeping in mind that there are people present in this demo session who don't know anything, okay, who don't know anything about this DRAM, DDR DRAM, okay. Why? Because this is the demo session. I need to start like this only, okay. Agree with this? Yeah.
Sure. Sure.
So yeah, yeah. So what is the DDR DRAM actually? So what is the DRAM? What is the DRAM? Okay. What is the, see, one more thing I'll explain you. So whatever you are seeing, the style of the teaching here, this will be continued throughout the courses actually. Okay, it may be a coding part, it may be a theory part, okay. Everything will be taken care like this only, okay. Whatever you are seeing, right, I'm opening some whiteboard and I'm explaining something and all. So this is how we are going to work in the normal sessions also, okay. So let's start with, so what is the DRAM actually? Dynamic random memory, correct. So dynamic random access memory, it's called DRAM. So what it stores? What it stores? It stores the data. How it stores the data? DDR is nothing. DRAM is nothing but, see, there is a one memory array. Memory array. If I take a simple example of this DRAM, see, there is a memory array. Correct. Correct. There is a locations in this. There is a locations in this. Each location can store respective bits depending on that. Okay. Depending on that. Let's take suppose in this location I can store only one bit. Think like that. I'll come to the cross one, cross six, or something later. So in each location, I need to store some data. Correct. This is the array. This is the array of some storage elements. Correct. This is the array of some storage elements. So this is called DRAM actually. This is called DRAM. We'll not go in depth. We'll not go in depth into it. We'll not go in depth into it. We'll just look at what is DRAM actually. DRAM is just storing element array of storing elements present in the systematic manner. Correct. Correct. So then what is this DDR actually? What is this DDR actually? Anyone have any idea? What is that a DDR?
It's a double data rate.
Yeah, exactly. Double data rate. Correct. So what happens in the double data rate? What happens in the double data rate?
So data sampled on the posits and the negatives. So
Exactly.
driving up.
Exactly. Exactly. So let's think that. So this is the clock, right? This is the clock. This is the clock. Okay. So think like we are doing some read operation and write operation. Where we are doing the read operation and write operation, we are doing in this memory array. What is this memory array now? DRAM, correct? DRAM. Present in memory array is present in a systematic manner. So this is the location, this is the location, this is the location, this is the location, where we are going to store the elements and read the elements and write the elements, correct? So in this is the posits, this is the negates, okay? This is the posits, this is the negates, this is the posits, this is the negates, something like this, okay? So what I'm doing here, simple example. So I'm doing a write example. I'm doing a write. Okay. Why? Where I have to write the data here first. So here and here. Okay. Okay. So what happens in DDR is double data rate. It is double data rate is nothing but in the pause edge of the clock and negate of the clock, we are going to store, read, and write the data in the locations of this DRAM. Okay. Okay. Suppose I am storing the data here. Okay. Suppose I am storing the data here. Okay. I'm sending one data here. Again, I'm sending the second data here, the negates of the clock also. So in the positives of the clock, I'm storing some data, writing some data here. In the negates of the clock, I'm sending some data here. In the again next positives of the clock, again I'm sending the data here. Okay, something like this. So this is how the double data rate works. This is the basic, very, very basic thing about the DRAM, DDR, DRAM. This is the DDR. So previously to the DDR, there was a single data rate. What was the single data rate? So uh, in the posits or negatives of the clock only, we were going to write some data or read some data. Suppose example, in the posits of the clock only, we are going to store some data, sending the data. If you toggle that data here, negatives of the clock, it won't take executed in the DRAM. This was called single data rate. Prior to this DDR technology, there was a single data rate actually. If you take the SRAM example also, SRAM, this is the same case. SRAM, SRAM, you know, right? Caches and all. Don't worry about that. SRAM will be covering in the next session actually. We'll go in depth from the basic only we are covering. From the basic only we are going to in depth. Okay, SRAM, how XRAM works, how DRAM works, and all. In the SRAM, the single data rate will have either in the posits of the clock or in the negatives of the clock, the data will be returned to the location or read from the location. So this is basic about. So this is basic about something DDR. DDR. Now I understand what is DDR DRAM. Now I understand what is DDR DRAM. Anyone have any doubt here? Anyone? Does anyone have any doubt? No, right? Right? Hope everyone understood this. I'm saying simple DRAM. What is DRAM? What is DDR DRAM? What is DDR DRAM? Next question, please. Next question. We got to know that the DRAM is some array element, some array of storing elements present in systematic manner. The DDR is double data. This is the technology actually. DDR is technology on which DRAM is working. On which DRAM is working. So the DRAM may be written and read the data in this location in the single data rate also, right? Single data rate also. But we are doing it a double data rate. In the posits of the clock and negatives of the clock also, we are writing and reading from this particular locations. Correct? So what we call this? This is the DDR is a technology actually. DDR is not a DRAM actually. DDR is a technology. DDR is a technology on which the DRAM is working. Correct? Am I right? Am I right? And you get to know that what and all the different technology we are going to use on that particular DRAM. Actually, in this particular DRAM is there, right? There are different technologies similar to this DDR present in the market where we are going to use them for the different applications depending on the requirements. Let's not go deep into that. Let's just understand what is DDR. When we come to that applications of the DDR, I'll be explaining what are the different types of DDR technologies we are present in the market.
So, Amit, actually, some of students are facing to, please allow to let me join
Yeah.
Zoom call.
No. They were in the waiting room actually. I allowed them. Yeah. Okay. I allowed. No problem. Okay.
Now,
Till
now,
now,
what? Now they will join, right? Now
yeah.
they can join.
Now they can join.
Okay.
They're
Okay.
joining. Okay. No problem. Yeah. Till now we completed what is DRAM, what is DDR, what is that particular DDR? DDR is a technology on which DRAM is working. Let's just understand what is DDR just. That's it. That's it. Okay. Anyone have any doubt in this particular till this point? Till this point, anyone have any particular doubts? Anyone? You can just ping in the chat actually.
No, you can continue on it.
Okay.
Yeah.
Okay. Okay. So next we'll come to demand in the DDR DRAM actually. What is the demand of the DDR DRAM? You already know that we are using the DRAMs in everywhere, correct? Everywhere, everywhere. So let's take a simple example, right? Simple example like where you are using where you are using the DRAMs. You are using the DRAMs in simple example DRAMs in mobiles and laptops. Let's say this is a simple example we'll take. Okay. Now I'll ask you a question. Now I'll ask you a question. In 20 years back, let's take a look at 20 years back. 20 years back, how many mobiles were advanced? How many laptops were advanced? Okay. What was the maximum DRAM capacity they were using in the laptops and mobiles? Hardly 1 GB or 2 GB. Correct? Am I right? And they were using oldest technologies, DDR oldest technologies. Correct? Correct. And and now you think yourself, you are using your personal laptops, right? Now currently you are using your personal laptops. Correct. And also you are using your work laptops separately when you are shifting to your office works. Similar to that, some of you may have your work mobile also and separate your personal mobile also. So now you are maintaining dual, I mean, dual mobiles or dual laptops in your day-to-day lives. Correct? In your day-to-day lives. In 20 years back, this was not the case. Actually, there were no this much consumption of these components, electronics components, mobiles and laptops. This much they were not using. Okay, there were some desktops were there actually in the back at that time. Okay, so now you think like in the 20 years back there were no consumption of that much devices in the mobile phones or laptops in the previous time. 20 years back there were no that much consumption. Correct. There were no that much consumption of electronics components. Okay, correct. And due to this, let's say consumption of the electronics components, there were no demand for this DRAM in the previously 20 years back. They were just adopting that DDR DRAM technologies actually. The DDR DRAM technology was not mature in that particular time, 20 years back, if you look at that time. Okay, DRAM was not mature at that time. That's why the demand was less for the DDR DRAM in the previous 20 years back. Correct. Now you try to think that we are in the 28-25. Actually, everyone were maintaining some dual components like mobiles and laptops. Now you think how many consumption is happening for this electronics components. Okay, in 2025. Okay, in 2025, everyone are using the multiple electronics components, right? In daily life. Correct. Now you think that everyone are using their multiple components, electronics component in their daily life. They are using mobile phones. They are using the dual laptops. They are using some smartwatches. They are using some IoT devices. Correct. They are using some server computers in their offices. Correct. Back in that time, there were no cloud and all. Let's not talk about the cloud and all. Okay, let's talk about the only mobile phones and laptops. Okay. Now in 2025, you are using so many multiple electronics in your day-to-day life. Due to this, there is a production increase of the DDR. The laptops and computers. If laptops and computers are increased in the production rate, then there is increase in the DRAM consumption also. Correct. There is an increase in DRAM consumption also. Correct. So if there is an increase in the DRAM consumption also, automatically the demand will be created for the DRAM. Correct. Automatically demand for the DRAM is increased. Correct. If I talk a little number about this, okay, from 2022 to 2025, the market for this DRAM was something around was some 75 billion, actually 75 billion. Correct. And if you compare next projection of this DRAM market, this is projected to the from 2025 to 2030. Okay, 2030. This is projected to some 300 billion dollars, actually, some $300 billion. Now you can compare at what rate the DDR evolution is happening, at what rate the DDR adoption is happening in the industry, and at what rate the DDR consumption is happening in the market. Okay, okay. Let's talk about some of the prominent, actually, in the back at that time. I told about this, right? 20 years back. So let's talk about 20 years back, how many companies were actually producing the DRAMs, actually. So, can anyone tell what were the prominent companies were there at that time? Anyone? Anyone? 20 years back, actually, like 2005, before 2005 or 2005. Anyone? Sorry, I'm not hearing you properly. She's trying to tell something, I guess.
Like had developed Intel and AMD, I think so.
Intel and AMD. Okay. So let's take about the Intel, and another is AMD. Let me take another example. Samsung. You left the most, actually, prominent one, actually. Samsung. Correct. And SK Hynix. Anyone know about this SK Hynix? SK Hynix.
Yeah. Our systems like before 2015 and 2010 will have this thing, SSDs.
Yeah.
Yes.
SK Hynix. This is actually prominent, one of the prominent company present in this DDR DRAM market. Okay. And one more company I can tell you is Micron. This is also one of the big giant in the DDR DRAM market. At back at that time, they're using some different technologies now, and they're also evolving in that DDR market. Still, also they are till in this point also they are actually very active in the DDR DRAMs. Okay.
Yeah, sorry to
Another,
interrupt. They
yeah,
mostly focus on Micron, focus on these DRAMs, this
yeah,
DDR and
yes, of
DHB.
yes, of course, yeah, yeah. If you look at any GPUs or any components in the market, you'll get one DRAM from Micron, actually. Okay. Another example I'll take, Rambus. Rambus. Anyone heard of this Rambus, actually? I can tell in another company is Microchip. Microchip. So these are the prominent, actually. These are the prominent, actually, companies present in the DRAM market. DRAM market. They were evolving like anything in back at that time only. Back at that time only. They started from DDR only. Okay. If I take some example, if I just pull up the some Chrome and start searching for this Micron DDR, see, again you'll get DDR DRAM, DDR SDRAMs. Again, if I pull up the Intel DDR, so there also you can see DDR DRAM. If I pull up again from the Samsung DDR, correct? Samsung DDR. See, again they are making the Samsung DDRs. DDR, actually, they are prominent in DDR. Sorry to interrupt. Sorry to interrupt that. So again, if I pull up some again one company, SK Hynix. SK Hynix, right? So let's see this. See, again, the SK Hynix is already producing the DRAMs. Actually, they were back at that time only. They were evolving in the DDR technologies. Correct. And one more example I can give is Rambus. Rambus. Actually, the Rambus created their whole separate RAMs only. Rambus DDR. Okay. See, DDR5. Already they are in DDR5 actually. Okay. If I take another example, microchip. Microchip DDR. See, they are also in the DDR market. So these were the prominent actually companies present in the DDR market at back at that time. Okay. Now in the 2025, along with these companies, there are also another companies present in the DRAM market, DDR market. They are actually backing this actually previous big giants. One of example I can give is Crucial. Anyone heard of this Crucial company? Anyone heard of this Kingston company? Okay. Anyone heard of this actually uh, DRAM actually? DRAM. Okay. These are the some of the companies actually now they are evolving. Now they are evolving. Crucial, Kingston, DRAM. Okay. If you think about, if you take example, Crucial is also backed by this Micron. Crucial's parent company is Micron actually. Okay. These are actually stepping into the DRAM market actually now current. If I show you some example, Crucial DDR DRAMs. See, these are the actually these are the examples I can show you from the Crucial. Kingston DDR DRAMs. See, these are the products actually from the Kingston actually. Kingston. Okay. They are very prominent in this now currently. Okay. Now, what I can say is there were these were the people actually present in back at that time doing the DDR evolution. These are the people doing the same evolution now currently. Okay. If I can mention one actually one more point here is like, so you all know that China is making the DDR I mean electronics components in the cheap at very cheap cost. Correct. At very cheap cost. Not cheap actually, at very cheap cost. Why they are making actually whatever you are seeing here, right? Whatever you are seeing here, right? These people are evolvedist. DDR1, DDR1, 2, 3, okay, 4, 5, okay. These people are made already this. Okay, these people played with this all and they are moving from this DDR to HBM and all. I'll tell you what is HBM and something like that. Okay, these people are moving, concentrating on DDR5 and HBMs. Correct, correct. Uh, does it mean that they are not focusing on DDR1, 2, 3? Yes, they are focusing actually. They are producing. Actually, they are producing. They are all constantly improving this DDR2 and 3s. Okay, all, but they are backing so much in DDR5 and HBMs. Now, what the China companies are doing, right? China companies are doing, right? They already have the technology. They already have the technology, and DDR3 1 to 4 is already matured actually, very matured actually. What is mean by matured actually? So they are using in the every component, every electronic systems are adopting it. DDR 1 to 4, every components are adopting it. So that's why they are called matured. Actually. Matured. Okay. They are very stable now in the market. So what the Chinese people are doing low cost, okay, low cost, they are producing it. They are producing it. What they are producing? DDR1 to 4. DDR1 to 4. That's why we get very, uh, very low cost for this DDRs actually. If you just pull up your Chromes and search for these DDRs, you'll get very cheap rates for some of the DDRs. Why? Why they are making in the China's only actually. Those are China made. Why they're China made? Because there are so many companies actually present in China which are making this DDR 1 to 4. Okay. They are backing the whole production in the for the world actually. So that much demand is there for this DDRs actually. That much the demand is there for DDR currently in the market. Okay. 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 Anyone have any doubt here? Anyone have any doubt? Why we are having so much demand for this DDRs and now?
Yeah, Amit, one joke from my side.
Yeah.
China with all technology designs with them.
Yeah.
Regarding
Yeah.
phone, I mean anything they have.
Yes, of course. Yeah. They are making every kind of electronics components actually.
Yes, that's great. That's great. But making cheaper, copying the
Yeah.
tech. Yes, that's
No,
mad.
actually, what matters is like infrastructure matters actually. You can take example of our India. In India, there is no that kind of infrastructure present in the India to manufacture those all components, TDI, DRAMs and all. If you take the China example, they are good in infrastructures.
And
Okay.
one thing I see, if I post any protocol thing, I got
Yeah.
a message from LinkedIn that if you want any manufacturing, please message me from China. They are calling.
Yes. 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 They are actually very prominent, actually very active in this kind of electronics components and all. That's
Yes,
why
yes,
they are making every kind of electronics component in China.
yes, yes,
Yeah. And one more thing is they need their support they are getting so much support from the government itself. In
yeah,
India, that's not the case actually. Correct.
yes, yes.
So
Yes,
that's the one point actually that matters so much. Okay. Yeah, already the tariffs war is going on from the Donald Trump and all. This is also affects the market actually.
yes,
Correct.
no, yes.
Yeah. This also affects the market. But
Like I,
also, but also there is a more demand for these DDRs. If you look at the uh, uh, if you look at the trend, the AI trend is going on now.
yes, yes, yes,
To build the AI computers, what you need? You need DRAMs,
yes,
DDR
yes.
DRAMs, correct?
Yeah, yeah, HBMs, which is a part of DDR.
DDR only, yeah. HBM, that's a part of DDR only, correct? You need
For
more number of DDRs
yes, yes.
to produce that high end laptops, high end PCs, high end mobile phones. Okay,
Mhm,
you
mhm.
need DDRs, of course, correct? So
Yes,
that's why there is a more demand for this DDR actually in the market nowadays. So it's better to learn this time. It's better to learn this DDR. Okay. Anyone have any doubt in the demand for this DRAM? Anyone got any doubts while explaining these points? Yes, please. Yes. No, right?
Yeah, Amit, like what I understood, like from previous 20-year back, only few demand is less due to that few companies only they are ready to manufacture the DDR, but due to now more demand due to yeah we are using dual phones, correct, dual mobile phones, smartwatch, and as well we are using like earbuds. So nowadays we wake up means all electronic devices only. So due to the demand is more, due to that new companies also created, new companies also coming to market to manufacture DRAM. Due to that, nowadays if you go for any company, so it's adopting DDR. That is the conclusion. Yeah,
Yes.
and
Yes.
yeah.
Yes,
Thanks,
of
thanks.
course. That's what I mean to explain in this actually previously. That's what I meant. Yeah.
Yeah, thank you. Yeah, thank you.
Yeah. Now I'll go to the applications of the DRAM. Now I'll go into the applications of the DRAM actually. Uh, Sachin, why? Anyone got access to this actually screen sharing? Okay. Okay. Now we'll go to the applications of the DRAM. You got to know that we are using the DDR DRAMs everywhere in the market, everywhere in the components, electronics components, and where and all we can use this DDR DDR DRAMs actually. DDR DRAMs. Anyone can give some examples. Some examples. Yeah. Okay. No problem. Yeah, I'll take the examples. So laptop also you are taking. Laptop also you are taking. Looking at the DDR only, DRAMs only. Looking at the specification of the DRAM. Correct. You're looking at the DDR specification of the laptops. Depending on that, you are taking. Correct. So I can take a laptops. Okay. Computers. Computers. Okay. One more example I can take is servers. 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 I'll explain one by one actually. I'll explain one by one how they are used actually. So another example I can take is consumer electronics. Consumer electronics. Correct. What is the consumer electronics? Consumer electronics is nothing but smartwatches, smartwatches, earpods, earpods, and some power banks, advanced power banks. Smart power banks are there. Correct. Smart power banks. So something like this, these are comes under the consumer electronics. Okay. And one more example I can take here is one more example I can take here. Anyone can give any example? Laptops, computers, servers, consumer electronics, and any other examples?
Fridge was washing machine. They are
Sorry?
using fridge and washing machine. They are using.
Yes, 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 yes. They are using it. That comes under the consumer electronics actually. And one more example I can take is IoT devices.
Earpods.
Yeah, that comes under the consumer electronics again.
Automobiles.
Yeah, automobiles. Automobiles. In automobiles, how are they you're using? We'll come to later. First, we'll take a look at what is where the in laptops you already know. You laptops already you know. In computers also you already know. There will be a CPU present in the laptops and all. Correct. This is the processor. Attached to this
Mobile
processor, there will
phones.
be
Mobile phones. I think.
Can
yeah.
power banks come?
Sorry. Sorry. Repeat it again. Come again. Hello.
Yeah, I think it is unfortunate. Like it was turned on, mic turned on, I think.
Okay. No problem. Yeah. How they are using in the laptops, computers, mobile phones? So they'll be using directly with the processors. If I take an example here, okay. So I'll be having some processor, correct? I'll be attaching this processor to the DRAM. I'm just looking into the brief architecture, not going in depth. Okay. We'll be using some DRAMs. Okay. Why they are used in the DRAMs actually? Say how they are used and what is the use of them using in the laptops, computers, mobile phones. So say if you are using some different applications at the same time, different applications at the same time. For example, I can take myself. I can take myself. I am pulling. I'm using the OneNote, Microsoft OneNote. Simultaneously, I am using the Zoom. So I open this whenever I start the computer. I open this both applications at a time. Okay. So here in the SSD, I have the codes of this both applications, data of this applications. What and all? Zoom and OneNote. Correct. Whenever I open them, the processor will tell the DRAM. The processor will tell the DRAM to open them. The DRAM doesn't have that data. The DRAM doesn't have that data of the SSD and the Zoom and uh, DRAM doesn't have the data of Zoom and OneNote actually. Where they request it? They request it from SSD. Then the data comes from SSD to the DRAM. Correct, correct, correct. So then the data will be coming from SSD to the DRAM and the data is present here now and then it can send the data back to the processor so that it can run the both the applications simultaneously. Suppose say we have the low configuration of this DRAM, 1 GB, 1 GB, okay, 1 GB. If you have the application size is bigger, Zoom application size is bigger and OneNote application size is bigger, it will take time for this to send the data from here to store the data and send it to the processor actually. So that's how the configuration makes difference in the speed of the computers and laptops. Okay, computers and laptops. And you can take one more, observe this one more point here is like the processor is directly connected to the DRAM, DDR DRAM, DDR DRAM. This is not connected to any other parts. This is not connected to any other parts. There comes another so many interfaces between this controller comes here. That's the other part of thing. But no other processor is connected to it. I'm not connecting to other processor and directly connecting it to the DRAM. No, I'm directly connecting the DRAM to the processor. Correct, correct. And that's why the speed is very fast in between the processor and DRAM. Correct. And I'm connecting the SSD from directly, not directly to the processor. I'm connecting the SSD to the first DRAM. And then the DRAM will request the from the data, DRAM from the data from the DRAM goes to the processor. Okay. You can ask one question. Why can't we connect directly SSD to the processor? We can't connect them. We can't connect them. Why? Because the data is present in the raw data here. Raw data here. The data is not ready to execute in the processor directly. You need to first make it executable in present by putting it in the DRAM. By putting it in the DRAM. And one more thing is, if you access data directly from the SSD, that's a very slow. That's a very slow. That's why what we do is we directly put the data from the SSD to the DRAM, then we will send the data to the processor. Okay. So that whenever the processor need again this data, this can redirect it to the DRAM and ask for the data of that particular application directly. Okay. Okay. That's how the DRAMs works in the normal laptops, computers, and mobile phones. Mobile phones.
Amit,
Okay.
like even the SRAM also do the same process, right?
Yes, yes. There is actually memory system is there. Memory system is there.
Okay.
Okay. Memory system is there. I'll explain it in the next session actually. That's the basics of that. So see here. So there is a processor. There is a processor attached to it. There is a L1 cache. This is the SRAM. This is the SRAM processor. If I start explaining about this SRAM cache and how the data works starting from this to this, this will be confusing. That's why I made it simple directly using the processor, DRAM and SSD. I'll be going in depth how the system works here, how the memory system works here from the processor to the SRAM to the DRAM to the SSD. I'll be explaining this particular concept in the first day of the session. That is tomorrow. That is tomorrow.
Processor have
Okay.
catch from
Yeah.
catch to SSD. Yeah, the conversion should be very fast.
Sorry, come again.
Yeah. I'm telling like processor have catchy L1, L2 catches are there. That
Yes,
are
yes. And that particular concept I'll be covering tomorrow.
sure. You
That
can go
particular, why? Because the demo session is something like we need to target everyone here,
overview. Yes,
everyone,
yes.
everyone here. So there are
Yeah, and
people
one
who
more thing,
don't know about the DDR
actually,
DRAMs.
yeah. So one more thing, actually, HRAM is most costlier. Like more, yeah, it will consume more. Obviously, one more question will come: why we are using DRAM in place of DRAM? Why we can't? If you go for any laptop, SRAMs will be in the KB only. It's not in GB. Like
It's
whichever top description is present in your laptop, mobile phone, that all are DRAM. Raw RAM is 4 GB. Why RAM? DRAM we preferred instead of SRAM. SRAM, why we are using inside system on chip is mainly to increase the bit performance. What type of performance? For example, I open Facebook application in my laptop. Again, I open PhonePe application in my laptop. Again, I open some other Word application in my laptop. But our DRAM is due to we are using less memory, 500 MB. Try to assume our DRAM is 500 MB. That time, obviously, our DRAM is engaged with all phone pay, Facebook, some other applications. But I'm trying to opening some more application like a Word document, but there is no space in DRAM. That time, our system is not wait until DRAM will be available, or not wait until I'm closing the phone tap, I'm closing the Google Pay, or any other application. It will work. How it will work? It is that time it is utilizing SRAM instead of DRAM. So that means SRAM and cache, these all are backup, like a backup. Whenever our DRAM is busy, somewhat it will communicate with directly. We can access with cache and SRAM. Why instead of DRAM we can't go SRAM? Is SRAM is most costlier. Six transistors needed in SRAM, single one is SRAM, but DRAM only one transistor, one capacitor. Area wise, DRAM will be less. Power consumption wise, DRAM will be less. Performance wise, also DRAM will be less. So, but coming to any mobile phone and laptop, compared to consumption, for power consumption, for example, try to assume you have mobile phone like 2 kg, you have mobile phone like around 100 grams, or one mobile phone 1 kg. But yes, they are saying 1 kg mobile phone we have, but it is a high performance. So you will purchase, it's very high performance. But 200 gram or 100 gram on mobile phone is there. It's bit lower performance compared to this, but okay, it will be means always users will purchase 100 gram mobile phone only. They don't purchase high because of speed. They don't purchase high-end mobile phone or high-weighted or area-wise big mobile phone. They don't purchase. So that is the market mentality now. That is the purpose. They are not going for SRAM. Basically DRAM, but SRAMs are present inside system on chip in KB format. That will be increase the performance of our laptop. Whenever our DRAM is busy, that time it will that time it will receive the data later on our cache memory finally send data to DRAM only. Later on SRAM finally sent to DRAM only. Yeah, yeah.
Yes, of course.
Thanks.
This is the brief of that actually memory system present in the laptops, computers, and mobile phones and SoC devices also. So this is the brief of this. Whatever the Chandan explained this is the regarding processor, SRAM, and DRAM and SSD. Okay, we'll be covering this whole memory system tomorrow. We'll be covering this whole memory system tomorrow. Today's agenda is only get to know that where DRAMs are using, where the DDRs are using, how they are using. That's it. That's it. Okay. Okay. So let's take. I explained about it, right? In the laptops, computers, mobile phones, and how they are mentioning in the. While you purchasing the laptops, you get to know always. Obviously, you get to know that uh, there will be mentioning of that particular RAM systems. Okay, just I pull up the Chrome and I open the laptops. There you'll get to see that. There you'll get to see that. See here. See here. This is the laptop actually. This is the specification of this laptop actually. So Core i5, Intel Core i5 processor is there. So 16 GB DDR4 is there. So DDR is a technology. They are using the 16 GB DRAM with the DDR4. 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 Let's forget about the 4 here. Let's forget about the 4. Only focus on DDR now. Only focus on DDR. We are talking in the in context of DDRs only. DDRs only. Okay. In every other applications, we will discuss only DDRs. Next, I'll tell you what kind of DDRs are using in the different applications. I'll tell it later in this point. Okay. Okay. Let's look at here. This is using 16 GB DDR4. And this computer is using 16 GB DDR4 again. Okay. And if we take some other examples, yeah, you can take Lenovo. This computer is using 16 GB DDR5. 16 GB DDR5. So that's how they are using in the laptops, computers, and mobile phones. Mobile phones. If I check directly about the mobile phones, I can check DDR, DRAM present in iPhone 15 actually. Let's take iPhone 15. Okay. So see here, the iPhone 15 models feature 6 GB of LPDDR DRAM. Let's forget about the LP again. Let's forget about the LP. Do not look at the LP. Only look at DDR5. Only look at DDR. Only look at DDR. They are again using the DDR. Correct. In iPhone 15, iPhone 15, they are using 6 GB of DDR5. Okay. Okay. Again, you can take one more point to mention here is they are using that DDR from Micron's DDR. They are Micron's DDR actually in mobile phones. In mobile phones, I'm talking about that too in iPhones. Okay. This is one example. This is one example. Again, the next point comes here is servers. Servers. Can anyone tell what is your understanding regarding the servers? What is your understanding regarding the servers? Anyone, real quick. Yes. What is your understanding regarding the servers? What you understand listening to that word servers?
Data storage center.
Data storage centers. One more point you can say regarding this. Any other points? Any other points regarding this servers? Okay, no problem. So I'll explain you what is servers actually. What is servers? What is servers? Servers are actually also store the datas also. Okay, and they can host some applications for their from them for their servers. How they are doing it? Let's take a simple actually basic analogy or some example, not analogy, so example only will take. See, this is my server center. This is my server center. Okay. I'll take one example. This is my server center. What kind of server center is this? This is the AWS server center. Server room. AWS server room. You know about the AWS, right? This is a service provider. Service provider. AWS, Azure. These are the service provider. Oracle Cloud. These are the service providers. Okay. This is the server room of this AWS server room. In this server room, there are so many compartments. In this particular compartment, there is a racks, racks. In this particular racks, there are CPUs present here. CPUs present here. Whatever you are seeing here, right? These are the CPUs. These are the CPUs. One particular CPUs. I'll take one CPU here, one CPU here, one CPU here. Okay. This is the motherboard of the CPU. Think that this is the motherboard of the CPU. Okay. There is a particular processor is there. Okay. And attached to it, there is a RAM. There is a RAM. Okay. If I take one example here, say some phone pay application is deployed here. Phone pay application is hosted here. If you are using some phone pay applications, right, that is deployed in this AWS server room, in this particularly this rack, in this particular CPU, they deployed this phone pay application. Okay, so that you can access it. Okay, okay. There is a processor connected to it, DRAM, so they are communicating to it. Communicating to it. Okay, okay. Again, these are not normal CPUs actually. These are not normal CPUs. We have, right, in our homes and offices, we have some desktops, laptops, and all, correct. We have some less configuration there, low level configurations in our homes, home computers, laptops, and all. But these computers not like that. These computers have high-end configurations. These computers can have high-end configurations. These processors are made particularly for this server PCs only. Okay. And if they are making this particular processor for this server PC only, then they are also making this DRAMs for this particular day. I mean, DRAMs, I mean, this particular server PC, right? Server PC, right? We can't use this kind of DRAMs in our normal laptops and normal PCs and okay, okay. This looks like our normal PC only. This looks like our normal PC only, but this is not. This is a server PC. If I just pull up the Chrome and show you, okay, server PC, okay, you can see here, desktop servers, okay. You can see here, these are the server PCs, just exactly looking like desktops only, but these are not desktops, normal desktops. You can look at here, the processor they are using is Xeon 2X E5 2680V4. Okay, this is the server PC. And again, you can see here, they are using some graphic, DRAM here, correct? DRAM here. I can show you here. So here, look at this server PC. So they are using Xeon 2X E5 2680V4. This is the particular processor they are using in this particular server PC. And also they are using 64 GB of DDR4 ECC RAM. Don't look at ECC now. I'll tell you what it is. Don't look at 4 here now. I'll tell you what it is. They are think that they are only using 64 GB of DDR4. In our laptops and office laptops and personal laptops and desktops, maximum we can have 12 GB or 16 GB, right? 16 GB, right? At worst case, we maybe have 32 GB in our gaming PCs. 32 GB of DDR DRAMs in gaming PCs. But they are using 64 GB of DDR4 in server PCs. Server PCs. That's why they are very different. Server PCs are very different. The RAMs using in that particular also very different. How they are different, I'll tell you later. I'll tell you later. When it comes to the different technology. Different technology. Okay. 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 And now come to here. Come to here. What is the next kind of applications we have here? Consumer electronics. Consumer electronics. What is consumer electronics now? Consumer electronics. Consumer electronics. So we may have smart watches, okay, and we may have AirPods, okay. We may have smart power banks, correct? Power banks, something like this, okay. There also they are using DRAMs. If I just pull up the Chrome and show you, present in the smart watches actually. I'll show you here. See here. So I'll go to the Rambus website. I can show you here what kind of DDRs they are using. What kind of DDRs they are using. I'll show you. Okay. See here. See here. So more specifically, the Apple Watch Sport is equipped with 512 MB of Micron's SD-RAM. Okay. While the Urban features 512 MB of Hynix Mobile DDR2. Urban is a smartwatch company brand actually. Smartwatch company brand. Okay. They're using the 512 MB of Hynix Mobile DDR2 DRAM in their smartwatches. Okay. Okay. There are different examples for this. There are different examples for this. You can say, look at here, LG Watch Urban
Yes,
Teardown.
one person is waiting in lobby. Can you please allow me?
Yes. At the same time, see here, LG Watch Urban is there, right? LG Watch Urban is there. They are using LPDDR3. They are using LPDDR3. Okay. Okay. Again, you got to know that what and all, where and all we are using, where and all we are using. We are using the DDR DRAMs in laptops, computers, mobiles, mobile phones, servers, consumer electronics like smartwatches, AirPods, smart power banks, not only normal power banks, smart power banks. And again, there is one more thing called IoT devices. In IoT devices, what they are using actually? They are using some processor, like processor, right? Processor, right? Some basic processor, right? I can show you
Oh,
one example.
some more people are facing issue. Can you please join? Allow join.
Yes, I gave it.
Okay, okay, thanks, man. Okay. So any setting is there like
So
directly?
I'm also checking that. I'm also checking that. Let
Okay, next
me.
time we will come up then. I think next class onwards, tomorrow onwards, because every time we are also engaged with class means every time
Yes,
we
yes,
can't give.
yes, yes,
So
yes,
next
yes.
time we will, if we'll be here, definitely some office call and all they will left. But next time, next meeting we will
Yeah, I
disable.
disabled it actually. I disabled it. And now they can join. I
Okay,
disabled
okay,
it.
then that's great. Thank you. That's great.
Okay, okay, okay. We were at looking at the applications of the DDR, right? So we are also using the DRAMs in IoT devices, correct? If we are
Uh,
using the
Hi,
DRAMs
Amit.
in, yes, yes.
How in a smart power banks they are using DDR application wise? Can you
Sorry, come again. Where?
in a smart power banks? Why
Smart.
we?
See, what the smart power banks are doing? What smart power banks are doing? They're calculating some. I mean, whatever the battery power is there, whatever the battery power is there, they're calculating it and they're sending it to the mobile phones. Actually, if you see it,
Okay,
they're sending the data to the mobile phones if the mobile phone is connected to it.
okay,
If this particular function need to be connected, you need a SoC there. Correct? You need a
correct,
small SoC there. If you need a small SoC work here, you need a DRAM attached to it. Correct?
correct.
Correct. So that's how they are using the DDR DRAMs in smart power banks. I gave you one example actually. This is one example only. You can take any examples. There are so many other products actually present using the DRAMs, consumer electronics. You can one said that a washing machine, right? One said that washing machine. There are also smart fridges are there. Smart fridges, fridge, correct? Smart fridges. They are sending the data from the fridge, what and all the vegetables are present in the fridge, and they are sending the data to your mobile in the office while you are in office, so that while going back to the home, so that you can take vegetables what you require, something like that. They are implementing this fridges. What you need there? You need IoT devices, correct? They are collecting some data. They're collecting some data. Again, they are doing some AI things here inside this. They're looking at the picture. They're setting a camera and capturing what and all the fruit items are there, what and all the vegetable items are there in the fridge, and they are converting the data into the text and sending it that text to the mobile phones. What you need there? Processor you need there. AI processor. What is AI processor? SoC only. Normal SoCs. You don't need high computation here. You need small SoCs. If you use that small SoC to support this SoC, you need obviously DRAMs. Correct? Correct.
Yeah,
So this is also one example.
thank you.
Yeah. Yeah. Where were we? We were at looking at IoT devices, right? IoT devices. Anyone give some one example for IoT devices? Any example for IoT devices? Any one example for the IoT devices, please?
Yeah, there are so many IoT devices. Like,
Sorry.
yeah, there are so many of IoT devices. Like what I'm saying.
Okay.
Like if you want
So I can take one example, Alexa. Alexa,
Alexa, it's a yeah IoT.
Google Assistants.
Yeah.
Okay, Google. Okay, Google. You will say use, right? Now and then. Okay, Google. Yeah, my phone is popping out, right? Google Assistants. One more example you can take is smart home. Smart home, correct? Smart home,
Yeah.
correct? So these are the IoT devices. These are the IoT devices. What they are using inside these IoT devices? What they are using inside this IoT device? They are using some processors, right? They are using some processor, right? Processor. What kind of processor they are using? I can take one example here. I can take one example here. So just search example processors used in IoT devices. So you'll get one of the some of the examples actually. So you can take ESP32. ESP32 in your college days you heard about it. If I'm not wrong, correct? ARM based processors. So Intel Atom, Qualcomm application processors. I can take one example, Intel Atom. Intel Atom. Let me search the Intel Atom now. Intel Atom processors. Okay. I'll directly go to the images. So here you can see Intel Atom processors. So this is the board actually they are using it. Intel Atom processor. This is the IoT device. This is the IoT device. They are not obviously they are not using this in the OK Google or some Alexa and all. They are using it some high-end IoT devices. High-end IoT devices. Something like farmlands, something like some right, IoT devices where and all the applications are there nowadays. Correct. They are using them. To make those IoT devices, they are using these processors actually. There are so many actually. There are so many processors actually. If you go to the NVIDIA website and search for the IoT device processors, you'll get so many. You'll get so many IoT processors. To run those processors, you obviously need DRAMs. You obviously need DDR, DRAMs. Correct. DDR, DRAMs. Now you go to know how they are using the IoT devices. IoT devices. Okay. Next, I'll come to automobiles. Where in the automobiles they are using the IoT, the DRAMs. DRAMs. Obviously, you all know that nowadays all automobiles are electronics, electrical. Correct. If the whole the automobile is electrical, obviously there will be some computers present in that. Let's take a simple example, Tesla. You already know Tesla is very smart. They can avoid the obstacles present before it. Correct. If someone comes on the path, on their path, it will stop at that point of time. Correct. Obviously, there is a running actually. If you heard Elon's talking about the Tesla, he'll say some Ubuntu is running in that. Some Linux machine is running in. Tesla is running in Ubuntu machine. To run this Ubuntu machine in the Tesla car, what you need? What you need? You need a PC there. You need a PC. To run this PC, what you need? Microprocessor. Obviously, if there is a microprocessor, obviously there is a DRAM present in that. Obviously, there is a DRAM present in that. I can take one more example actually. You know Mahindra road assistance, Mahindra road assistance, so that cruise control and all, correct? Cruise control. Once you set the cruise and if you stop pushing the accelerator pedal, so it will go automatically itself, following the lane, following the route. What is going on there? They are using some computation, right? They are using some computation. To run that computation, what you need? You need some small machines there, PC machines. To run these PC machines, what you need? Processors. To run this process, what do you need? DRAMs. One more example I can take. In that particular Mahindra car only, there may be some ECUs will be present. What is ECU? ECU. What is ECU? Engine control unit. Engine control unit. Engine control unit. Correct. In that engine control unit, What is it calculating? It is calculating at what rate the engine is running, what is defects present in that engine, and it is sending the data to the dashboard of that driver seat. Correct. What it is doing? It is sensing the sensing the obstacles present in that particular engine and whatever the issues of present in that particular engine from the sensor, and computing it, sensing the data and sending it back to the dashboard of the driver seat. Correct. Correct. That's how the ECUs works in the car. To run this ECU, what you need? You need a small machines there. Small machines. To run these small machines, what you need? Processor you need. To run this processor, what you need? DRAM. Obviously, whenever you are using some processor, obviously keep that in mind that you need a DRAM, that particular point. Okay. 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 Now you got to know that where and all we are using the DDR, laptops, computers, mobile phones, and servers in the server PCs, consumer electronics like the smartwatches, earpods, power banks, and IoT devices like Alexa, Google Assistants, smart homes, and farmlands IoT devices we are using, and automobiles. Okay, automobiles. How they are using automobiles? I gave you Tesla example. I gave you Mahindra car example. I gave you a ECU example. Engine control unit. In this engine, whatever the faults present in, it will sensing to the sensor. Correct. Sense that data and send it to the ECU. ECU will calculate and send it to the dashboard. This is how the DDR are applicable in different applications. Okay. Anyone have any doubt here? Anyone have any doubt here till now? Anyone? Anyone have any doubt? Yes. In mobiles, LPDDR is why they are using LPDDR. I'll say till now we only looked at DDRs are only using. What kind of DDRs are using in different applications? We look at different types of technologies using the DRAM. Now we are going to that. Okay. Okay. Now we all got to know that. DDR is the prominent, one of the main technology we are using in the DRAMs. Correct. Say this is my processor, this is my laptop, and there is a processor. Okay. I am using a DDR DRAM. It may be a DDR 1, 2, 3, or 4, something like that. I am using a RAM here. Okay. DDR DRAM here, and this is the processor actually. Okay, I'm using it. No problem. Why we are using it? So obviously, laptop and computers, so we already use this processors and related DDR DRAMs in that. No problem. They are connected and they are working fine. I'll take one more example here. Mobile phones. If I use that particular DDR DRAM, whichever I am using in this my laptop, whichever using in the DDR DRAM, if I put that same DDR in the mobile phone, does it work properly? Obviously, it will work. But I want whether it will work properly or not. What is the requirement of the DDR DRAM if I use that in the mobile phones? What is the requirement of it? The requirement is it should consume less power. It should consume requirement to use the DDR DRAM in mobile phones are less power, less power consumption. And one more is it should give high throughput, high throughput. It should give high throughput. Okay, but 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 and also the size should be compact. Compact. To satisfy all these conditions, there comes a DDR technology called LPDDR. 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 Okay. 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 What is LPDDR full form here? What is LPDDR full form here? So LPDDR full form is low power double data rate. Double data. What they are doing, the name suggests that they are reducing the power consumption of this particular DDR. How they are doing it, we'll look at it later. Why? If I explain how they are reducing the power consumption in the DDR, it will be very complex for you now currently. You won't understand it currently because they are using some reducing the signal pins and reducing the some cycles in that, refresh cycles, and that's something. They are doing a lot of things there in the LPDDRs. Now just understand where they are using, why they are using LPDDRs in mobile phones. I can take one more example here, smartwatches. Smartwatches. In smartwatches also you need DDRs. What kind of DDRs you need? You need DDRs which consume less power here. Then again, which kind of DDRs I should use? LPDDR, correct? LPDDR. LPDDR. Correct. Correct. Now you got to know DDR is different. DDR is different. Normal DDR. This is the normal DDR. LPDDR is different. LPDDR is different. I make a list here. Technologies of DRAMs. What is the first technology? DDR is one technology. Again, in this DDR1, 2, 3, 4, and 5, something that like that comes. And next one is LPDDR. Correct? And LPDDR versions are there. LPDDR1, 2, 3, 4, and 5. Okay. And next one I can take example is GDDR. 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 Now I'll explain what is GDDR here. What is GDDR? Graphic DDR. Graphic DDR. Why this graphic DDR is used? Where they are used? Let's take some example. Say you already know NVIDIA, GeForce, RTX, GTX, some graphic cards are there. Correct? Correct? Correct. I'll just pull up NVIDIA GPUs. NVIDIA GPUs. So these are the graphic cards actually. These are the graphic cards. In this graphic cards, they are using the GDDRs, not DDRs, not LPDDRs. They are using the GDDRs here. Okay. Okay. I'll tell you how they are using the GDDRs. How they are using the GDDRs. Why they are using the GDDRs, particularly in the graphic cards. Okay. The requirement for this GDDR to run the graphic card is to run the graphic card. This is the graphic card, right? This is the graphic card. This is the graphic card. They are using the GDDR here, and requirement is you need high throughput, and it can consume more power. No problem. Can consume more power. No problem. Okay. It can produce more heat. No problem. More heat. No problem. I don't have any issues with that. But what I want is the throughput should be high. The throughput should be high. Throughput should be high. Why the throughput should be high here? Why the throughput should be high here? Let me explain you that. Explain you that. See, in this GPU, particular GPU, okay, there is a processor actually, GPU processor. GPU processor. Okay. What exactly the GPU cards are used for the graphics center? Graphics center. See, there is a main processor present here. Main processor present here. Some Intel or AMD, some processor i5, i3. This is separate processor. This is running normally our computer. How the normal computer runs. This also runs the same, exactly same. This also exactly same. It runs. What it does, extra calculations are the rate. Extra calculations are the rate. It will send those calculations to the graphic cards. For example, I can say there is a one game called GTA 5. GTA 5. Okay. You just click the GTA 5 and it is showing loading. Loading page. Loading. Correct? Loading. Loading. What it is doing actually, the CPU, you gave the command for the main processor to run the GTA 6 and it opened the application for the normal RAM. From the normal RAM, it is opened the application and it sent the data from this SSD. From this SSD, it sent the data from the DRAM and from the DRAM, you're sending the data to the CPU and from this, it is rerouting the data to the graphic card actually. Graphic card. Graphic card. It is sending the commands to the graphic card processor. Graphic card processor. While the game is loading, present DRAM, I mean GDDRs present around it. GDDRs present around it. It will load the whole data of that particular game. Particular game. Whatever the data present related to this GTA 6, it will load that data to the this particular GDDRs. Okay. Okay. Now you know that the graphic cards are hungry machines. What hungry machines? Data hungry machines. Why they are data hungry machines? Why they are data hungry machines? Because this processor is very powerful. This processor is very powerful. Okay. Okay. It need continuous data input. Continuous data input. Continuous data input. If you use normal DRAMs like this here, it won't work. It won't work. It won't work. The data will be, short. The data shortage will become for the data shortage will happen for this processor, GPU processor. That's why we use GDDRs here, GDDRC, so that it can throughput the high data, throughput the data, more throughput the data. Okay, so that it can send the more throughput data and send it to the GPU processor, and the GPU processor calculates and sends it back to the main processor, and main processor will execute that. Now you understand why we are using the GDDRs in the GPU graphic cards and how they are working. Okay, how they are working. So this is how the GDDRs are using the, the graphic cards are using the GDDRs. Let me just show you. Okay, okay. Graphic card by I'll go to the Amazon link here. Okay, just look at here. Just look at here. See, this is the NVIDIA Quadro T1000 4GB, 4GB graphic card.
You mean, think you. Okay, okay, understood. Yeah, thank you. Okay, sorry. It's my end.
Yeah, we are using NVIDIA Quadro T1000 4GB. This is the graphic card. In that graphic card, they are using GDDR6. GDDR6. Nowhere in the graphic card you can see we are using the DDRs. Nowhere in the graphic cards you get to see the usage of the DDRs. You only get the GDDRs in the graphic cards. GDDRs in the graphic cards. Okay. Anywhere you can search. Anywhere. Any graphic card you take a look at. Take a look at any graphic cards. You get the GDDRs here. GDDRs. See here. This is the RTX A6000. They are using 48 GB GDDR6. 48 GB GDDR6. Even though the GDDRs are putting the more data to the processor, still they are using 48 GB of GDDR6. Okay. Now you got to know how powerful is that graphic cards and how powerful is that GDDRs. Okay. 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 How they are powerful, we'll look into it next class, actually. If I extend it, it will consume more time, actually. Okay. Okay. Now you got to know GDDR. What was our one more technology? HBMs. HBMs. What are HBMs actually? What are HBMs? What are HBMs? So if I elaborate it, if I elaborate it, HBMs. So this is nothing but high bandwidth, high bandwidth modules. High bandwidth modules. How different are these HBMs from normal DDRs? How different are these HBMs from normal DDRs? See, if I tell you about the normal DDR, you already got to know that in normal DDR, we are using 2D arrays, memory element arrays. This is present in 2D, right? 2D, right? 2D, x-axis and y-axis. But in HBMs, the memory arrangements are not like this. They are arranged in 3D format, 3D arrangements. 3D, 3D arrangements. How they are arranged in 3D arrangements? Okay, they are arranged in x-axis, y-axis, and z-axis. X, Y, and Z. They are arranged like this. The memory elements are arranged like this. Let me just pull up that. Okay, this is the diagram actually. Okay, take a look at it. Take a look at it. See, this is the HBM die. This is the HBM die. This is the HBM die. One HBM die. And these are connected through each other. If I take a look at this particular HBM die, one HBM die, I can call it as this is a one 2D array, right? One 2D array, right? I'll put this 2D array like this. Okay. Beneath that, I'll put one more 2D array and one more 2D array and one more 2D array. Combining this will become one HBM die. One HBM die now. One HBM die. Now you got this is x-axis, okay? This is y-axis and this is z-axis. Okay, they are arranged in 3D form. 3D form. How they are connected? They are connected through through silicon wires. Through silicon wires. Through silicon wires. So all this array, right? This is the one array. This is one array. Similar to that, there is another array beneath this, beneath this, beneath this. Another array, another array, another array. They are connected through this. Why they are connected through this? To give the high bandwidth. To give the high bandwidth. At a time, if you work with one array, you will get less data. Similarly, think like if you work with so many arrays similar to this at the same time, you'll get more data, right? More data, right? For example, for analogy, we'll take at particular 0th nanosecond. At particular 0th nanosecond, we are reading the data from the one array. You will maximum we will get 1 bit data. Think like that. Okay. In HBMs, let's take an example. We are having similar arrays beneath one by one each other in the number of 4. In the number of 4. I mean, 4 arrays are beneath one another. One another. 4 another. So at the 0th nanosecond only, if I use the HBMs, I can access 4 bit of data. 4 bit of data at a time. So throughput is more, right? Throughput is more, right? Bandwidth is more, right? Bandwidth is more, right? So similarly, this one die is there. Actually, this is one die. If I connect that one die beneath one another similarly, this is one die, this is another die, this is another die, this is another die. Okay. I connect them through silicon wires, through silicon wires. This is one technology actually. This is the technology they are using in the HBM die through connect them to each other. Through connect them to each other. You can't separately make a PCB and put those HBM. Not like that. Not like that. We can't achieve the high bandwidth using this. If we put one another and use the through silicon wires, we can make the high bandwidth here. We can make the high bandwidth. Where they are using actually? Where they are using? Where they are using? So think like in graphic cards we are using GDDRs. In graphic cards we are using GDDRs. So to make the high performances graphic cards to put the calculate the more data. You are in AI era, correct? AI, correct? You need AI computers now. AI computers. What AI computers are doing? AI computers are doing nothing but computation of so many data. Computation of many data at a time. Many data at a time. Correct. Correct. More than this also, they are doing the in the AI computers. More than GPU, more than graphic card, they are using the AI computers. Correct. In this particular application, we need HBMs. HBMs to achieve the high throughput. High throughput. Okay. So that more data calculated at a time. More data calculated at a time. More data can be fetched from the SSD or some other places and send it to the processor. Correct. Correct. Now you got to know where they are using HBMs. Okay. 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 And till now we completed like where and what are the DDR technologies actually present in DRAMs. So one is DDR, normal DDR, double data rate. One is LPDDR, nothing but low power double data rate. One is GDDR, this is main graphic double data rate. Okay. One is HBM, nothing but high bandwidth modules. Okay. This is one example. There are so many other technologies also present there. Okay. One is video DRAMs, VDRAMs. And previously, before this LPDDR and all, Rambus introduced their own their technology actually. That's called DRAMs, RDDR. That's nothing but a Rambus double data rate. Double data rate. They introduced in the previously, but they failed it. They failed in marketing and they failed in adoption actually. Why? Because the RDDR was very costly for the licensing and the complications were there. Even though they made a high throughput and less power consumption DRAMs using the RDDR, it was very tough for the markets to adopt it. Why? Because licensing. I mean, more money for the licensing and all, and complex fabrication processes and all. That's why the RDDR was failed in the market. Okay, these are all the prominent technology we are using in the DRAMs to achieve the different kind of DDRs. Now you got to know where exactly we are using different kind of DDRs. In DDR, we are using a normal computers and all. Okay, we are using the RDDR. Leave about the RDDR. Actually, we are not using the RDDR in current industries. In 2020, before 1980s, they were invented this RDDR. After that, this RDDR vanished from the market. No one are using this RDDR from 2005 only. Okay, LPDDR they are using low power DDRs in the mobile phones. Okay, in the mobile phones, in the smartwatches, in the IoT devices, they are using LPDDRs. Why? To reduce the power consumption. To reduce the power consumption. And GDDRs they are using in the graphic cards. And HBMs are they are using in the AI computers. AI computers. AI computers. Okay. Anyone have any doubt till here? Anyone have any doubt till here? Okay. Please. Anyone have any doubt till here?
Yeah, Amit, like what we understood is DDR is a one thing, but we have DDR different technologies. So DDR and LPDDR and GDDR and HBMs. So in our laptops we are using DDR, and in our mobile phones we are using low power DDR, and in some graphic cards we are using graphic DDR, and some of AI applications we are using high bandwidth models. So that we got it. Yeah, thanks, Amit.
Yeah. Now we stick to the DDR. Why we are sticking to the DDR actually? See, DDR includes every concept whichever present in this, whatever present in this other technologies. If you understand DDR, you can switch to any kind of technologies. Any kind of technologies. You need to understand only basic things like DDR. That too, if you understand a DDR3 or DDR4, you can switch back to any other technology and work on any other DDRs, any other DDR technologies, any other DDR technology. Okay. You need to understand only one technology, which is basic one, that is DDR, that to DDR3 or DDR4. No one are using DDR1 and 2 nowadays. Don't move to DDR1 and 2. They are most of them using DDR3 and DDR4 and DDR5. DDR5 also not using so much here. This is not matured yet in the market. Most of them you are using are DDR3 and DDR4 in the normal day-to-day life electronic components. That's why we are doing the course on this DDR3 and DDR4. If you understand this DDR3 and DDR4, you can switch to any technology and understand the any technology of the DRAMs. You need starting point, which is DDR. In that particular also DDR3 and DDR4. If you understand only DDR3 also, it's enough. You can switch to any kind of DDR4 or DDR5, any kind of technologies. I'll explain it. This is the evolution of the DDR. This is the evolution of the RDDR. This is the evolution of the LPDDR. There is the evolution of the GDDRs. There is the evolution of the HBMs. Different versions of these technologies are there. Similarly, LPDDR 1, 2, 3, 4, 5. GDDR 1, 2, 3, 4, 5 also is there. Similarly, HBMs also 1, 2, 3, 4, 5 also is there. If I take a simple example, look at here. Look at here. Okay, let me refresh it actually. Okay, there are so many technologies present here. Okay, one I can show you here is like in microns examples. Microns examples. Okay, so that's why we are focusing on actually DDR3 and DDR4 in the current course. If you understand any one of this DDR, you can switch back to any other technology and you can serve. Okay. Okay. Now we got why we are focusing on DDR. Anyone have any doubt till here? Anyone have any doubt? Anyone have any doubt? See here. See here. This is the HBM2E from my. This is from SK Hynix. SK Hynix. This is HBM2E DDR. This is the version of the HBM2E. You can see here. You can see here. HBM1, HBM2 Gen 1, HBM2 Gen 2, HBM2E, HBM3, HBM4. There's a different versions of this. This is the evolution of HBMs. Similarly, evolution of DDR also is there. GDDR also is there. LPDDR also is there. I'll explain in the tomorrow class actually. That's the agenda of the tomorrow class, first class. Explaining the memory modules and memory system and different evolution of these technologies. Okay. Anyone have any doubt? Next, I'll explain the what and all the course we are offering on this DDR3 and DDR4. What and all the course we are contents we are offering in this course on this DDR3 and DDR. Anyone?
Still, anyone have any doubts? Please ask. Like actually, I know it's we are going with very all concepts. So that is the purpose. I know it will be really difficult to digest all the concepts, but no issue. Recorded access also available. But it's very good information. So as already know, you people like I don't know who all are working in DDR. They also don't know really these all are applications. DDR will be like if DDR means we are thinking like only mobile phone also we don't think laptops. Okay, because when we go to purchase any laptop, then only we can see oh DDR is there. But now today see not only laptop is like a 10% of consumers in DDR. Laptop is a Out of 100% DDR useful is laptops are I can take like 10% consumer, remaining 90% are different. Mobile phones, automobiles, IoT devices, like electronics consumers like earbuds, like the earbuds and washing machine, fridge, smart power bank system. So all are a smart keyword is there, smart house, smart. Those all DDR will be useful. Means till this point we learned like only the laptops only, but today we learned like laptop consume is only 10%, remaining all dependencies 90% is other. So that is the today main demo conclusion. Demo conclusion is what is the first DRAM. DDR is a, most of our think like a DDR is a memory. DDR is a memory. No, DDR is not a memory. DRAM is a memory. But to achieve that DRAM, we are using different technologies. So that one is DDR is one technology, LPDDR is another technology, GDDR is another technology, HBM is another technology. First, next onwards, if anyone asked, because I also took lot of students interview. They also have very good knowledge in DDR. I'm asking, DDR is a what is mean by DDR? They're saying DDR is a memory. Then really, I'm thinking why DDR is it? Then what is meant by DRAM? DRAM also memory. And wow, it will be DDR also memory, DRAM also. That clarification first you need to learn. DDR is a different, DRAM is different. So that today agenda, first we explain what is DDR, DRAM. Next, why demand? 20 years back, there is no demand. Only few companies working on fabrication. Now, most demand is more. Each person handling two to laptops, two to mobile phones, two to fridges, two to washing machines, like the two to smartwatches. Demand is more. Obviously, marketing, lot of companies will create it. Nowadays, you search any company along with DDR. Any company, Cadence along with DDR, Synopsys along with DDR, Analog Devices, Texas Instrument, NXP Semiconductor, AMD, Intel, Qualcomm, Synopsys, Micron, any company you mention along with DDR, every company working on DDR. Why? Demand is more. Demand is more. So that is the purpose nowadays. Every engineers looking for DDR and PCI technology. Yeah, I need to learn DDR. I need to learn PCI. So that demand we understood. Next, we entered applications. We understood where and all it will be useful. Mobile phone, laptops, electronic consumers, automobiles, IoT devices. So these things we done. Like that, multiple things are there. We target max 80% consumers. Like that, till 20% are there. Like that, other devices. Next, we enter DDR technologies. Like DDR is not only every product, they are not only using DDR. Some mobile phone, they are using LPDDR. Graphic cards, they are using GDDR. AI tools, AI laptops, they are using HBMs. That is the today main agenda. What is the demand is there? Why I need to learn DDR? To this point, you who all are learn, definitely you get to know some clarity about DDR. DDR, one question to Alex, if I told to coach everyone is our students only. So I know DDR theory part. I know DDR theory part. I asked simple. Their question is like either okay, which frequency your DRAM is working. They can't able to answer, but they are saying I know I have theory knowledge. I'm saying your DDR currently useful in which project? Either it will be laptop, either it will be mobile phone. They can't able to answer. If I am taking interview for DDR, if they have any knowledge, most of profiles are have theory knowledge on DDR. My first question for them is I will give addressing table, JDAC addressing table. You people know 2GB, 4GB, 8GB. Can you explain this addressing table? Till this point, no one will clearly explain that addressing table, but still they are in their resume, they are mentioning DDR theory knowledge we have. That and all, really, if I am an interviewer, that I don't tell you, don't know JDAC document, you are saying JDAC, DDR1 website is there, DDR4, DDR5, around 4 pages. If you go that, I know DDR means that's completely wrong. DDR is not like only learning some websites, learning some chat. We need to go and we need to spend more time on JDAC document. If you are good at JDAC, then you can say, I have good knowledge on DDR. So if you have good knowledge, theory knowledge in DDR, like that, next I will ask, who all are good theory knowledge in DDR? I will take small interview for them. I will ask some questions. If you clarify, because if you clear that interview, then only I will allow for coding. Because some students are really, sir, I don't want part one. We have two modules, theory part and coding part. I will, if you need to allow coding part, because I know in this batch, most all are our previous students only. They know me very well. I know me very well. So they know how I will be. So I know how they will be. First, I will take interview. Then if you clear that theory interview, then I will access for coding part, because now you don't know theory, but I am discussing coding time, I am explaining some concept, means you can't catch, means again it will be lost for you. That we don't want that thing. Okay, the next, Amit, can you please complete within 15 minutes this course, part one, part two?
Yes,
So
yes, yes.
but it's really, it's very, very, very helpful. Really, it's very, very good. So very good explanation and all. So please complete within this fast. Yeah, thank you.
Yeah. So all you got to know that we are offering this DDR course. As I explained, there are different technologies. Once you understand any one technology, you can switch back to any other technologies and learn that quickly. If you understand any one technology to switch back to any other technology, you hardly need 1 or 2 weeks in your companies to work on that. You can directly say, I can work on any technologies if you learn any one technology. That's why we are focusing on some basic technology, which is DDR, and that too DDR3 and DDR4. Okay, okay, okay. Our course is divided into two parts actually, part one and part two. In part one, there is a DDR3, sorry, there is a spelling mistake actually. I'm sorry for that. So there is a DDR3 and DDR4 for DRAMs, which includes complete concepts of DDR3 and DDR4 and intro to the DDR5 and HBMs. Okay, okay, okay. Every concept of DDR3 and DDR4, we are including in that. We are explaining that. Once you understand every concept of DDR3, within 3 to 4 days, we can complete a DDR4 completely from beginning only. But to complete at DDR3 from the beginning, it takes minimum 20 days. Minimum 20 days to complete a DDR3. Once you understand the DDR3, to complete the DDR4 from the beginning, it hardly takes 1 week for me to explain to you. Explain to you only. If you read that, it may take barely 4 to 5 days. That's why I'm saying you start from the basics, and if you learn basics, everything is built upon the basics only. That's why I'm telling we are offering this course on DDR3 and DDR4 and intro to the DDR5 and HBMs. What and all the changes they are making in the DDR4 to make the DDR5, and what and all the changes they are making in the technologies to make the HBMs. Okay, okay. And one more point is part one is completely based on theory. Completely based on theory. Why? Because we need to understand each and every concept present in the DDR3 and DDR4. What and all those concepts I'll explain in the next slide. Okay. Okay. Just keep in mind that the complete part one is theory part. And we need minimum 30 days for this DDR3 and DDR4. Minimum 30 days for the part one actually. You can say part one. Part one will be completed in minimum 30 days. Okay. Okay. There will be a buffer days for this. Buffer days, which means there may be some emergency for me, some emergency for some Chandan, and there may be some technical glitches will be happening in some random days. So those all not, I'm not calculated those days. I'm only calculating 30 days. We need, if I continue from this day 1 to day 30, I completely consistently do the classes daily. It takes 30 days for me. No need to worry that if you miss any classes in between, we can give you recorded access. Recorded access. No need to worry that. Okay. And then part two comes here is part two is the coding part, complete coding part, complete coding part. And specifically that particular coding is made for verification purpose also and RTL design also. What RTL design we are doing, what verification we are doing in that, I'll tell you in the next slide. Actually, there is architecture. I'll explain you. Okay. 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 And prerequisite is for the part one, you don't need any prerequisites. You don't need any prerequisites. If you don't know anything about the DRAM, it's okay. That's why I covered today, actually. Basics of that DDR. Okay. Only thing you need to have is waveform analysis. Waveform analysis. Okay. And ability to read the spec sheets, specification sheets. Basically, mainly we are focusing on this JDEC specifications. If you ask what is JDEC, what is JDEC? JDEC is an organization which is making the which is making the specification sheets common for all the companies. Common for all the companies. Every company present out there, they should follow the JDEC document so that their particular produced components can be used in any other components. Say my HP laptop is there, my Micron DRAM is there. I can use Micron DRAM also. I can use Samsung DRAM also in my HP laptop. How? Because they are the Micron producer, and Micron is also following the JDEC specification, and Samsung is also JDEC specification to produce that DRAM. Okay, understood? Understood. There is an international standard for that. For any electronics out there, there is an international standard for those, and that will be made by JDEX. JDEC is an organization. Okay.
Yeah,
If
this is actually very important point what you mentioned. See, for example, if you go to any laptop service center, so they can suggest like we will replace instead of 2 GB DRAM, 4 GB DRAM, then the RAM, then your laptop performance will increase. See, you are saying like his service guy is saying like instead of 4 GB RAM, I will replace 8 GB. Then your laptop performance will be good. But for example, your laptop when you purchase it will be Micron means he don't place always Micron only. He will go with some of less cost. For example, Scandesis like that somewhat less cost, some crucial like that he will purchase and he will put 8 GB. But your laptop support crucial DRAM also. Your laptop support Micron DRAM also. Why? Because every company using same specification to develop DRAMs, that is the JDAC. If different companies using different specification means definitely your laptop not supported, because every some company working different configuration, other company working different combination. Finally, we can't use different RAMs to your laptop or your laptops or your computers. So that is the purpose of every company using standard JDEC spec only. We are also using JDEC spec. This is very important because you already know, everyone have experience. In your laptop, you can replace DRAM possible. So, yeah, thank you. Yeah, please continue.
Yeah. And in the part two, you need solid understanding of the DRAMs, any one technology, DDR3 or DDR4, you need solid understanding of that. Whatever theory part we are doing in the part one, you need that. If you don't want to attend the part one, it's okay. But before starting the part two, you need to have complete understanding of the DDR3 or DDR4. Okay. Okay. And specifically in part two, we are focusing on DDR3. DDR3. What specification we are, focusing, I'll tell you in the architecture. Okay. And another prerequisite is proficiency in Verilog and system Verilog is must for the part two. You need to know Verilog and system Verilog. Okay. We are not using any scripting languages here. Don't worry about that, because this is not the company project we are working on. Okay. Okay. And you need to have minimum Verilog and system Verilog and experience in UVM, universal verification methodology. Since we are doing the verification project of this, you need to have a verification methodology experience and familiarity with verification tools, whichever you want in your personal laptops, whichever verification tools or EDA tools you want to install, you can install, and you should be proficient with that particular tool. That's the what prerequisites I want for part two. Okay, and I'll come to the course content. For part one, I'll be going in order of this list, actually, in order of this list. Memory system arrangement in SOCs. How the memory systems are arranged in the SOC. Whatever I was explaining, right? How the DRAMs are connected to the processors, how the DRAM is connected to the SSD, and how the caches are included in that, how they are communicating to each other. That's the concept we are going to target in the particular first concept, first one. Okay. And then next comes here is memory cell architecture. Okay. Memory cell architecture. And then next comes here is different technology of the DDR. Whatever I explained, right? GDDRs, LPDDRs, Okay, HPMs. Okay, their evolution is there, right? Their evolution is there, right? That part I'll be covering here. Different technology of the DDRs. I'll be explaining again all the technologies, where they are used, why they are used, and then I'll come to their evolution. What is the differences between DDR1, DDR2, DDR3, HDDR, LPDDR1, LPDDR2, LPDDR3, okay, GDDR1, GDDR2, GDDR3, something like that. Okay. Next comes here is DDR packaging. DDR packaging is like for your laptops, you will be having different kind of memory types, DDR memory types. Okay. In your normal computers, you will be having different memory types. Those are called DIMMs actually. Dual inline memory modules, single inline memory modules. In that dual inline memory modules also there are different types. In servers DIMMs also they are using different kind of DIMMs in server RAMs. That part I'll be covering in the DDR packaging types. And next comes here DDR addressing. You know, right? In the DRAM, there will be banks, there will be banks, there will be some rows and columns. There will be different number of banks, number of bank groups. In DDR4, you will have the bank groups. In DDR3, you don't have bank groups. Okay. You have ranks, correct? You have page size. You have page size. You have number of locations present in one row, number of present locations present in one bank, how much data you can store in one bank, how much data you can store in one chip. If I give a 8 GB DRAM, how to divide that into a number of DRAMs? How many number of chips I need for to make a one DRAM? Okay, this is what we are covering in the DDR address. Okay, next comes here is timing parameter. This is a very important part. Why? Because in the every other DRAMs they are using the timing parameters, which are very strict from the JEDEX, They can alter it. There are some timing parameters which we can, the companies can alter it. But from the JEDEC, there are some specific timing parameters which are very particular fixed. That timing parameters, we can't change them. Those parameters we will be looking at here. And then comes the pinout description. For this particular DRAM1 chip, what are the pinouts are there? How many pinouts are there? What are the pin ins, pin outs, and pin in outs? We are discussing in this part. And then comes the important topics, delay lock loop. Why delay lock loop is used in the DRAMs? And then comes the PLL, phase lock loop. Why PLL used in the DRAMs? Where it is coming from? The PLL comes from controller only. Controller and to the PHY to the DRAM. So PLL will be calculated in PHY. PHY sends the PLL. This is the reference clock for the DRAM. This extracts the PLL and makes the DRAM. This concept will be making here. After learning the DLL, after learning the PLL, we'll be looking at some examples like this. And next comes here is on-die termination. What is the concept of on-die termination and why they are used? In which different technology, how they are used. So you know that LPDDR we are using less power. So this is one reason why it is consuming less power in the LPDDRs. It is used less in the DDRs. It is used more in the LPDDRs. Also, there is a ZQ calibration concept. We will be looking. Okay. Okay. So next I'll come to the next part. So again, part one, in that, again, there is a concept called mode registers. This is very important. To configure the DRAM, you need mode registers. You should send some signal to the DRAM and tell how you should behave. This is done by mode registers. The multi-purpose registers are present in DRAM. Why they are used, how they are used, will be explained. And refresh in DDR. You all have a familiarity with refresh, self-refresh. Okay, refresh for entry, refresh exit. Okay, there is a concept of refreshes in DDR. And power down mode. Okay, when you put your laptop in the sleep mode, The DRAM also in the on only, but it goes to the power down mode. Power down mode. The DRAM will be running it's on its own. Whenever you open your laptop again, the processor will send some signals and it will activate this DRAM. Okay, this is called power down. How it is working, how they are sending the signals, and how it is detecting it. We are looking at here power down mode. And next comes here is precharge and its types. Precharge. You already familiar with precharge. Auto precharge, precharge, write precharge, read precharge concepts are there. Command table of this particular DDR3 and DDR4. Command tables. Command tables, you will be following some commands for particular that command should be sent from the controller. What signals you need to make high and what signals you need to make low. That will be done in the command table. And next comes here is DDR state diagram. State diagram, you know how the DDR should behave from the initialization to the ending of the transaction of the DRAM. Okay. Once you learned all regarding in context of DDR3, then to make those concept in DDR4, it is very easy. To understand all those concepts in DDR4, that's very easy. What happens is DDR4, they increase the throughput and they are increase the throughput and they are making the less power consumption here. How they are making less power consumption, how they are making throughput more. Once you understand all this, you'll be able to relate them to the DDR4. In DDR4 also, again, we are explaining all those concepts, whatever I explained in the above. Okay. That time we'll get to know what kind of the concept variations we are making from the DDR3 to make it DDR4. Okay. Understand? That's about the part one. So if I come to the part two, okay, I'll directly go to the architecture and explain you. Next, I'll come to this part slides and I'll explain you what and all the particular features we are going to cover in the verification. Okay. What and all the particular things we are covering in the verification actually. Okay. Can you? I'm active, right? You can hear me, right?
Yes,
Yes.
Amit.
Yeah,
Okay.
yes.
Okay. This is about the part. This is what we are building in the part 2, in the coding part. Understand? Okay. So, since this is a part 2, we are doing it everything in coding part, and I'll explain you one by one what we are doing. So, DRAM memory module, you are seeing here, right? This is what we are taking from the Micron VIP. Micron VIP. VIP is nothing but verification IP. Okay. We can't use the actual DRAMs because the DRAM is nothing but analog mixed digital component. We can't use it hardware to verification of purpose. That's why we are making use of some VIP. VIP is nothing but a verification IP. We are using it for the verification purpose, and we are taking it from Micron. This is nothing but a DDR3. Verification IP from Micron. Okay. Next, we are implementing the DDR interface. And connecting them. This is one part. Next, I'll come to the memory controller subsystem. Actually, this is memory controller subsystem. In memory controller subsystem, we are making use of AXI slave. So basically, we are interacting with the memory controller and DRAM using the AXI. You can use Wishbone also. You can use PCIe also. Okay. Since we are strong in our RJ Semiconductor service is very strong in AXI, that's why we are making use of AXI master. That doesn't mean we are not using the ready-made code here. We are again writing it. Don't think like that, okay? Okay. So we are using AXI master here. AXI master, AXI interface, AXI slave. Okay. This we are building and first we are testing it. AXI is working fine. Then we will go to memory controller subsystem and setting up the AXI slave. And then we are going to write the DDR IP. DDR IP. And then the PHY block IP. PHY block IP. Okay. What and all the functions is done by DDR controller? We are implementing it in DDR controller. And what and all the functions the PHY block is going to done, it will be done in the PHY block. Okay. Okay. And we are implementing a DFI interface. DFI interface here. DFI interface is used to make the communication between the DDR controller and PHY block. Why? Because this is running at different frequency. This is running at different frequency. This is running at PLL frequency. Okay. This is running at CPU frequency. Whatever the CPU is running at, this is the frequency where DDR controller is running at. To transfer the data between commands from this to this, you need some DFI interface to make the sync between them. Understand? Once we set up this, we'll be bringing up this whole system. AXI, memory controller subsystem, and DRAM. Okay. Once we do this all, then we'll be writing some sequence blocks and checking the whole setup manually, whether the bring up is correct or not. Okay. We are sending some sequences, some basic sequences, and checking whether our bring up is correct or not. Then we'll coming to the verification part. And we'll be doing the monitor block, where this monitor is extracting the data from AXI interface, actual data, and one more monitor block where it is extracting the data from DDR interface. Okay, this is the expected data. This is the expected data. This is the actual data coming from, and we'll be sending to the scoreboard, both of them. Okay, and we'll be verifying them in the scoreboard. Okay, and same monitor data will be sending to the coverage and actual data to the coverage, and we are making the coverage block here. Okay, together this and this. See, let me erase it all and explain it. Okay, together this everything makes test bench. Together these all blocks makes TB. Understand? Actually, in companies, what happens is they'll be having some AXI master VIP from purchased from any other companies, and they'll be implementing some test benches here only in this AXI master only, AXI master VIP only. They'll be implementing some monitor, some coverage blocks, some sequencer block, and to that sequencer block, we'll be connecting some sequences. Then we are sending the sequence to this. Here also we are doing the same. In the master VIP, we are implementing in this particular block only. We are implementing some sequencer. We'll be implementing some monitor. We'll be implementing some scoreboard, and we'll be implementing some sequencer and everything in the AXI master VIP only. And using the SV concept, will be deriving from them. Sequence block will be derived from this, and we'll be sending driving the sequence to the sequencer. Okay. This is what we are going to do in the part 2. Okay. And in particularly, I'll explain you what are the features we are going to cover. Okay. So here you can see initialization sequences. To start the DDR, you will be having some DDR3. You will be having some initialization sequence. To run that initialization sequence, there is some set of commands are there. Power up sequences, CKE assertion, mod racer programming, DLL locking command, ZQ calibration. Everything comes under the controller block. controller block plus PHY block. In this controller and PHY, we will be driving the signals to the DRAM.
And one more thing is this all covered in theory part. So who all are people saying I know theory means if you have good knowledge on ZQ calibration, mode register programming, CKE assertion, DLL clock command, power up. See, you people know DDR is nothing but some pins, some class for class, not like that. How can we power up sequence? This all already we done in part one theory part. Now we are going part two. So, but you join part two only, then really you don't, once again you are asking to explain ZQ calibration means then it will go to another, instead of 40 days it will go to 60 days, so that again it will be timing issue will come. So into, actually we also need to, one product we are giving to you people means we also need to give in on time, right? Then only you also feel happy. That is the purpose. We are also following that some steps. So if like that delayed means, then again you also feel finally it will be, oh you told 3 months but it will consume 4 months, like that we don't want. That is the purpose we are saying. Part theory part, means this all point, then we allow coding part. Yeah. Okay.
Yeah. Yeah. That's why in the coding part, we'll be writing directly commands for this power up sequences. Whatever logic required for the power up sequences, we are driving in the, we are writing in the control block and PHY block and driving the DRAM. We don't want explanations here. Why, what happens in the power up sequences of when we have to turn in this sequence, when we have to turn off this sequence. If you know that concept, then you'll be able to write the logic for this power up and sequences. Similar to that, CK assertion and mode register programming and DLL locking system and ZQ calibration. CKE nothing but clock enable. When you need clock enable, when you don't need clock enable. In the power down mode, you don't need clock enable. That's a concept. If you know that concept, then you can write the logic for that in the controller to try the command, and it will come to the PHY. PHY will send the actual signals to the DRAM. Then we'll come to the command schedule. Command schedule. We'll be having so many different commands, right? Activation command, read command, write command, read with auto precharge, write with auto precharge. These are the different commands driving from the controller. The controller do the command scheduling here. Okay. The controller do the command scheduling, and according to that commands, the PHY block will be driving the DRAM. Then comes the timing management. You already got to know that. We'll be explaining the timing parameters in the part one. According to the timing parameters, we'll be implementing the every logic. If I take some simple example, power up sequence, when you give the power to the DRAM, you need to give some time to recover it. Okay, that's the one example of the timing management. We need to give exactly some time. If you give more time, it will be out of order. The controller will be not control. DRAM will be not in our control. Something like that. That's why we need maintain timing management here. Okay. Next comes here is basic memory operations. Basic memory operations. Normal read, normal write, recharge all bank, recharge. Okay. Okay. These are all logics written in controller block. According to that, signals will be generated, commands will be generated and sent to PHY block, and PHY block actually generates the signal to the DRAM. Okay. Okay. These are the features we are implementing in the controller and PHY. If I go one more bit extended version of this our project, I can tell we can be able to write with auto precharge, read with auto precharge, burst chop. Someone was saying burst chop actually in the class. So burst chop, we are using the burst chop. We are implementing the burst chop logic and we are driving the DRAM. Okay. Write leveling. Write leveling comes in the concept of power up sequences. To train the DRAM initially, whenever you open the DRAM laptop, the DRAM will be activated. That time, the write leveling will be happening here. Next comes the on-die termination. When you need the on-die termination, why you need the on-die termination, when we need to implement that. What is the timing parameters comes under the ODT so that we can control the ODT? What are the other operations? See, whenever a ODT is off, so there will be other functions which are not applicable for this ODT. Whenever ODT is on, the other functions will be working properly. That's why I'm saying theory part is very, very important. Okay. Next comes here is we implemented PHY block and controller block now. Now we are implementing the test bench and in that AXI master, AXI slave component will be writing. Okay, we'll be writing. See, every component we are writing in the our own only. But it will be some we already prepared for it, and we'll be typing directly. And don't worry about the queries. We'll be clearing every queries of yours. Every queries of yours. Don't worry about that. Okay, and next we'll be implementing test bench environment for verification. Test bench environment for verification. You got to know that we are implementing two monitors. One is sequences and one scoreboard and one coverage. If needed, we can complete the assertion block. If needed or if possible, if time persists. Okay. Next comes here is DFI interface component between the controller block and PHY. Already I explained. And AXY sequences with multiple test cases. AXY sequences with multiple test cases. Something like aligned address, unaligned address, aligned, unaligned. Okay. We can implement some test cases like out of order test case, out of order. Okay. Some decode error test cases, some slave error test cases, something like that. Okay. We'll be implementing so many test cases regarding the AXI sequences in this project. Okay. This is all we are going to complete in the part 2. Okay. Okay. This particular part 2 may take more than 35 days. More than 35 days. Why? Because we are implementing each and every component on our own, and it may take more than 35 days. Okay. Okay. So this is what we are covering in the part 1 and part 2. Anyone have any doubts regarding this? Now you can ask your queries and I'll be clearing.
Yeah, but one thing I can say, like it's really great, Amit. Like I appreciate your effort. I appreciate your delivery point. I appreciate your what you come up with today. Like really, it mean to lot. Like lot of things you covered. Like I don't know how much students will utilize this, but it's really a lot of thing it will be like. But okay, time is expanded. We thought 1.5 hour, 2.5 hour, but really, I think 15 days researches you explained in 2.5 hour like that your demo. It's really great. I appreciate your thing. Yeah, thanks. So still anyone have any doubts? Please ask. Please ask. So not only here, like after class also, if anyone have any doubts, please ask. Yeah.
Yeah, go ahead. Please ask. Obviously, I am sure that you'll be
Okay.
having
Yeah,
so
I
many
think.
questions in your mind.
Yeah.
So you can
Yeah.
ask them. If not possible, you can just ping in the WhatsApp group. We'll be clearing them. That's it.
Yeah. I think today we will stop the. Please stop recording. This is enough, Amit. So then we can come up with doubt discussions and all. No need.